Let's start with the UI section. More specifically, we're going to talk about UI update cost, and within that scope, we'll focus on UGUI. Now, why UGUI? If you've seen our recent performance report, we published it a few weeks ago on our blog, you might recognize the pie chart I'm showing here. Every year, we release what we call a performance blue book. It's based on aggregated data from a large number of commercial projects tested on our platform. We track things like Unity version adoption, feature and module usage rates, real-world performance characteristics. And here's the key takeaway. Despite the availability of other UI frameworks, GUI, NGUI, and even additional Unity toolsets, in commercial production environments, UGUI still dominates by a wide margin. Because of that dominance, we understand its behavior very well. And over the years, we've accumulated substantial optimization experience around it. So when we talk about UI update cost today, we are specifically talking about UGUI. One quick clarification. Today's focus is strictly on main thread UI logic cost. UI obviously affects rendering, batching, and other subsystems, but that's outside the scope of this session. We're zooming in on the primary UI update nodes you see in the profiler. Traditionally, when profiling UGUI, we pay attention to several key functions. The first one is the well-known Canvas.SendWillRenderCanvases. This represents the cost of updating UI elements. In simple terms, if you have complex UI, meaning a high vertex count, and those elements update frequently, you'll see a stable, often significant cost here. This is one of the most common UI bottlenecks, but it's also a well-covered topic, so today it won't be our main focus. Next, we have Canvas.BuildBatch and the long call chain that follows it. In earlier optimization guidelines, we emphasized the idea of dynamic static separation. The concept was straightforward. Separate frequently updated UI from static UI to avoid unnecessary mesh rebuilds. However, in modern Unity versions, and by modern, I mean versions that have been around for several years, a significant portion of BuildBatch work has been moved to worker threads. What we now often see is the main thread waiting for worker threads to complete. In most recent production projects, even if teams don't strictly follow dynamic static separation, BuildBatch rarely shows up as the primary bottleneck. So the natural question is, do we still need dynamic static separation? Let's pause that thought. We'll come back to it. Now we reach today's real focus, CanvasRenderer.SyncTransform. This node appears at the same hierarchy level as SendWillRender and BuildBatch. Let me show you a real example. This test was conducted on a Snapdragon 8 Gen 2 device, a flagship class chip. We monitored two metrics. First, rendering update batches, which represents overall UI update cost. Second, the call count of SyncTransform. Notice something important. We're not plotting its time cost, we're plotting its call count. And even from that alone, we can see a strong positive correlation between SyncTransform call count and total UI update time. When SyncTransform calls increase, UI update cost increases almost proportionally. If we inspect the call stack inside update batches, we see something interesting. In addition to SendWillRender, we also find SyncTransform, SyncWorldRect, SyncClipRect. Individually, each of these nodes has very low self-time, much lower than SendWillRender, much lower than BuildBatch. So why are we discussing them? The reason is simple. Although these nodes are typically low in execution time, if their call frequency is high, it can still lead to a significant increase in the parent node's rendering.update batch time, ultimately raising the overall execution time. Let's now look into why these nodes tend to have high call frequencies in many projects. The first and most common cause is changes in transform information. When UI elements transform data changes, it triggers a call. In some games, especially MMOs or multiplayer combat games, UI elements like HUDs may move due to the player's camera angle or character movement. In such cases, a single movement can trigger a large number of transform changes for UI elements. For example, in a vehicle combat project, you can see a large number of friendly and enemy units' HUDs in the distance. These UI elements include names, health bars, and other details, all of which may cause hundreds of transform calls after a single movement. While this is a basic, typical phenomenon, we've also observed high SyncTransform calls in projects where UI elements don't move frequently. Let's explore other potential causes. We conducted an experiment using a 3-layer structure: Grandpa Canvas, Father Canvas, and Son Canvas. focusing on the father canvas. Adjustments to UI elements at this level will often affect other elements in the hierarchy. For example, changes at the father canvas level could trigger sync-transform calls on sibling elements, e.g., 10 calls for text components at the same level, 5 for the parent canvas, etc. In our experiment, when instantiating UI objects, we observed 16 sync-transform calls. This occurred because 10 sibling text components and 5 from the parent canvas were all triggered by this instantiation. Next, when we destroyed a UI element, we observed 10 sync-transform calls, affecting only sibling elements in the same canvas. For UI elements activated with SetActive true, we saw 16 calls, similarly affecting itself, sibling elements, and parent canvas elements. From these results, we hypothesized that the sync-transform call is linked to changes in the GameObject's hierarchy within the canvas. To validate this, we used a less common API, setSiblingIndex, which alters the sibling index of elements in the same canvas. This also triggered the sync-transform call. The takeaway here is that frequent instantiations, activations, and destructions of UI elements are common operations, particularly in scenarios with elements like UI particles that need to be activated or hidden frequently. These operations can trigger additional, unexpected performance overhead. It's important to note that these API calls only take effect when they are actually needed. For example, if an element is already active, calling setActive true again won't trigger any change. From a performance optimization perspective, we recommend separating frequently instantiated, activated, or destroyed UI elements from static UI elements, placing them in different canvas layers. For instance, one canvas for dynamic UI elements that need frequent updates, and another for static elements. This separation ensures that dynamic elements won't impact the performance of static elements, offering a more efficient solution. Additionally, this design approach imposes certain requirements on the UI structure. Specifically, intermediate canvas layers shouldn't carry too many UI elements to prevent unnecessary performance bottlenecks.